Hi everybody, Dr. Bianchi here, and in this lecture clip, I am going to be covering the basics of the t-Statistic, a new family of statistical tests that we're going to be talking about for the next couple of weeks. So the first part of this video is kind of a repeat of what we've talked about in class already, where we introduced the t-test, we talked about its purpose, why it exists, and in what kinds of situations we would be using a t-test over a z-test. So I'm going to quickly kind of review the nuts and bolts of what we spoke about in class, and then I'm going to focus on a complementary follow-up measure to the single sample t-test, which are our measures of effect size. Those are going to give us a measure of the absolute magnitude of a treatment or intervention effect, and they typically are reported along with your t-test results. We will talk about Cohen's d, which you're already familiar with, and I will also introduce two other measures of effect size that you see in the literature. Okay, let's go ahead and just kind of re-jog our memory about the t-statistic. Okay, in short, a t-statistic is used in situations where we don't know the population standard deviation. Okay, that value about the population, the spread of scores, is unknown to us. In this kind of a situation, we're going to use sample data to test out our predictions about that unknown population. We will use the sample standard deviation to estimate what the population standard deviation is likely to be. Okay, so we're using our sample to make all of our inferences about the population. Okay, so when we were doing the z-scores and the z-test, you always had information about the population standard deviation and the standard error of the mean. Okay, with the t-test, we're going to use that when we don't know the population standard deviation. All we have is our sample data, and we have to go off of that. Okay, so the t-statistic is an alternative to the z-test, and we are still going to be calculating standard error, but because we're using our sample to estimate the population standard error, we now refer to that value as the estimated standard error. Okay, S subscript M. Okay, this is the estimated, whoops, sorry about that. This is the estimated standard error. It's going to be used in place of the real population standard error because we're unable to compute that. Again, we don't have the population standard deviation. Okay, so how do we calculate the estimated standard error? It's going to be the denominator of our t-statistic. I suggest that you use the variance-based formula. Okay, not only is it in some ways easier to use, but also it's going to be necessary for some different versions of the t-test that are coming up where you have to use the variance-based formula in order to go through with the math. Okay, but for now, you should be familiar with the fact that with the single sample t-test, we are using the sample to estimate the standard error, okay, the discrepancy between the sample mean and the population mean. And we're going to calculate that value using this variance-based formula. If you haven't already downloaded the formula sheets for the t-tests, go ahead and get those downloaded, print them out, write them down. I've organized all of the mathematical formulas for each t-statistical test for you. Here is our t-statistic formula. Okay, the t-statistic uses that estimated standard error of the mean in place of the true population standard error. Okay, so our denominator is an error term, and our numerator is simply the mean difference, okay, between the sample and the population mean, which we do have access to or is hypothesized. Okay, overall, the t-statistic is used to test a prediction about an unknown population mean when the value of the standard deviation is also unknown. Okay, this is your t formula. For our results to be significant, statistically significant, we're going to want to get large t values. Okay, we want our error to be small And we want our sample to be really different from the original population that it comes from. Degrees of freedom is something that comes up, and degrees of freedom can be one of those things that's really complicated to explain in all its depth and detail. For the purposes of this class, all you really need to know is that degrees of freedom is going to be involved in a lot of our math, and it's just the sample size minus 1, okay, n minus 1. So degrees of freedom is intricately connected to sample size. Okay, we call it the degrees of freedom. Why is this called this? Well, if you look at the math, when we actually calculate sample variance, it requires that we also compute the sample mean as well. This has an impact where only a certain number of scores in the sample are independent. There's restrictions placed on which scores can vary, blah, blah, blah. It's really not necessary for you to know all of that. It's simply n minus 1, okay, degrees of freedom. Here's the t-distribution. It's more variable. As our sample size goes up, our degrees of freedom also go up, and our t-distribution approaches more normality. Okay, with smaller sample sizes and lower degrees of freedom, we get more of a flat top to the curve. Okay, so I handed out the t-table in class. There's a copy of it on D2L if you do not have the copy from class. But you will be using the t-statistical table in order to hypothesis test with the t-test. Okay, it's a family of distributions, and there's there's basically a separate kind of curve for each value of degrees of freedom. So on the left side of that table, you're going to see the degrees of freedom, which you're going to need to know for your study. It's always n minus 1. That's going to tell you where to look on the table. In my class, we're always going to be running two-tailed tests at the 0.05 alpha level. Okay, so we'll be using the t-table from here on out for the next couple of weeks for all of our t-statistical testing. Okay, you absolutely need that table or you won't be able to answer most of the questions in this chapter. Okay, so here is our one sample t-test, okay? And this is assuming that the null hypothesis is true, right? This is assuming that the sample is not in any way different from the population. Okay, so here's our sample mean minus our population mean, and down below we divide by that estimated standard error. By definition, the null says that t will be 0, okay? If we get t-values close to 0, that supports the null hypothesis that nothing interesting is going on. Our sample mean is very closely identical to the population. Our treatment hasn't changed them. There's nothing different about them. When we get larger t-values, either in the positive or the negative end, that's going to be evidence for the alternative hypothesis, okay, that our treatment or our intervention had an impact and changed the sample, and they are now noticeably different from the original population that they have been drawn from. Okay, a one sample t-test is used to test a prediction about a population. We're just using one sample to do it. Okay, I'm going to skip past this. Okay, so when we go through our hypothesis testing, we're going through the same 4 steps. Okay, we always state our hypotheses, our alpha levels 0.05. Then we will use the t-table to locate the critical region, okay, using the degrees of freedom. We will calculate the t-statistic for our sample, and we will make a decision about whether or not to reject null. Okay, if our t-value falls in the extreme tails of the curve, we'll reject the null and we have evidence for the alternative hypothesis. However, if we get t-values close to 0 or pretty small, we're going to be less likely to reject the null hypothesis. Okay, so I had walked through this example on infant research in class. I'm not going to go through it again. If you missed that example, please take time to download the slides and walk through it. Okay, I kind of spell the whole thing out. But here's just an example of this t-distribution. And just like with the z-test, we're going to have our critical values that are dictated by the t-table. Okay, we use the degrees of freedom in order to find those critical values. And they mark the boundaries for the critical areas on both ends of the curve. Okay, in this study, if I got a t-value for my sample that was greater than 2.3, or below negative 2.3, I would reject the null hypothesis, and I would say that that sample is significantly different from the original population that it came from. However, if my t-values fall in the middle of the curve, I don't have enough evidence to rule out the null hypothesis. Okay, I cannot say the sample is significantly different from the original population that they were drawn from. What are some assumptions of the t-test? Well, like most of our statistical testing, all the values in the sample are independently observed. Okay, they're not related in any way. They're independent measurements. And also that the population sampled is normally distributed. Okay, remember, the larger our samples, the better guarantee we have of normality, okay, normal distribution. One thing about the t-test is that it's a robust statistic, which means we can have some slight violations against these assumptions, and the test will still work pretty well. Okay, but ideally, we are sampling from a normal population, and we are getting as close to as possible normally distributed data. A great way to check out if your data is normally distributed is to generate a histogram. You'll be able to see that really easily if it's normally distributed or if it's looking kind of wacky. Okay, a couple questions here. When the sample size is small, less than 30, what happens to the t-distribution? Take a second to look through those. Okay, remember, when our sample size is small, that means our degrees of freedom is smaller. Okay, and our t curve is going to be flatter and more spread out, okay, than the normal z distribution. Okay, that goes all the way back to here. Okay, as we have a larger sample size, we have a higher degree of freedom, and our curve approaches normality. Okay, true or false? By chance, two samples selected from the same population have the same size, okay, 36, and the same mean. Okay, the mean score is 83. That means that they will also have the same t-statistic or the same t-result. Okay, go ahead and look at the formula for the t-statistic and see if you can figure this one out. Okay, false. Although a lot of those values are the same, the two t-values that we get are unlikely to be the same because the variance will still be different between the samples. Okay, so, okay, yeah, they have the same sample size, they have the same mean, but the spread of scores likely will vary from one sample to the next. Okay, the other question was asking you, compared to a z-score, a hypothesis test with a t-statistic requires less info about the population. Okay, true. The t-statistic does not require that you know the population standard deviation. However, to calculate a z-score, you need that info or you'll get stuck on the math. You won't be able to complete the formula without that info. Okay, so in class we went through both of these two t-test examples. Okay, if you missed that, all of the solutions are in the notes of the PowerPoint slides. You should be able to take this information here about this sample and compute a single sample t-test. Okay, the first step is to calculate the estimated standard error and then use that in the denominator of the single sample t-test formula to get a t-value. Once you have the t-value for your sample, you then use the t-table to look up the critical values. Okay, you would look up using the degrees of freedom what the critical t-value is on both ends of the curve, compare it to what you obtained for your sample, and make a statistical decision about whether or not to reject the null hypothesis. Okay, in this example that we did in class, we saw how a small sample size of 4 made it really difficult for us to achieve statistical significance. However, with a larger sample size of 16, this study became statistically significant. This sample was now noticeably different from the original population it was drawn from. So you should be able to solve both of these problems successfully. If you missed class or you missed this part of the lecture, go through and make sure you can solve these using the t-test math formulas. I'm assuming that everybody is there right now and can make the appropriate statistical decision using the t-table. We're going to now transition into measuring effect size. Okay, effect size follows up after our t-test, because remember, with a hypothesis test like Z or T, it's just telling us whether the treatment effect is greater than chance. Okay, is it greater than chance would predict? But it doesn't tell us how practically meaningful the size of the effect is. And we've talked in class about how very small treatment effects can be statistically significant. Okay, therefore, results from a hypothesis test, whether it's Z or T or any other hypothesis test, should always be backed up by a measure of effect size. Okay, effect size allows us to get an absolute measure of the treatment effect, the treatment impact. Okay, and Cohen's d is the one that we are the most familiar with because we've already seen it. Now remember, with the single sample t-test, we only have our sample. We don't have our population parameters. Okay, the way we used to calculate Cohen's d required us to know those population values. So instead, we're going to call this estimated d because we're using our sample data to estimate Cohen's d. And we'll use the sample data in order to do that. Okay, what is the mean difference between the sample and the population? And what is the sample standard deviation? Okay, this is the key difference here, is that we're using the sample standard deviation to estimate Cohen's d. Why? Because again, we don't have the population standard deviation. We don't know that value. Okay, so you should have this formula down or have it on your formula sheet available to use. Okay, this is just showing you how we could compute Cohen's d for the baby example that we walked through in class. Let me just move this out of the way. Okay, so here, remember with the infant example, the baby spent 13 seconds looking at the attractive face, but the null hypothesized that out of that 20-second trial, the babies would prefer the attractive and unattractive face equally. So they should look at each face for 10 seconds. Now that didn't happen. The babies spent more time looking at the attractive face, specifically 13 seconds. So we can calculate Cohen's d for the baby study. Okay, the sample mean was 13 seconds. The null hypothesis predicted it would be 10 seconds. And the standard deviation is 3. Okay, this gives us a Cohen's d of 1.0, and that is a large effect. That means that the baby's preference for the attractive face was a full standard deviation above what the null hypothesis predicted. Okay, here's what the null hypothesis predicted. Okay, 10 seconds looking at each face. Here's what our sample actually did. Okay, 1 full standard deviation bracket above the mean. Okay, large effect size. Now, I want to introduce another measure of effect size that we're going to be using in this class. And this one can be a little bit more difficult to understand. Okay, conceptually, people get a little bit confused with this one. This measure of effect size is called percentage of variance explained. Okay, and the calculation is really straightforward, but the concept of explained variance is more complex. Basically, what we're looking for here is when we look at behavior or any kind of outcome or change in behavior, how much of that is accounted for by our treatment or our intervention? Okay, how much of that can we explain? Okay, we're determining the amount of variability in scores that can be explained by our treatment. Okay, so if people change 10 points or 15 points on average, how much of that is due to our treatment and not due to other factors, okay, like measurement error and the fact that just over time things tend to change? Here's the calculation for R squared. Okay, conceptually, we are taking the variability that our treatment can explain, and we're dividing that by the total variability in the study. Here's the math to do that. Okay, t squared divided by t squared plus degrees of freedom. Okay, we just simply plug in our obtained t values for the sample, and we go through this math. And here are the shorthands for interpreting r squared. Okay, the percentage of variance explained, r squared. 0.01 is a small effect. Anything around 0.09 is considered medium, and 0.25 is large. Okay, again, these are shorthands for interpretation. Okay, easy to calculate. Single equation, you plug in your t-values, you get r squared. Okay, and we're going to do some practice with this in a moment. Here's our infant example yet again. Remember, our t-statistic for that example was 3.0. There were 9 babies in the study, so we have 8 degrees of freedom. And here we're going to go ahead and calculate r squared. Okay, 3 squared over 3 squared plus 8. Here's the math. We end up getting 0.52, okay, or just about 53%. What is this telling us? This is telling us that over half of the variance in the preference, the looking time of babies at the faces, is explained by that preference. Okay, we can account for 50% of the variance, okay, 53% to be precise. That's how much our study can predict. Okay, another easy way of thinking about this is if you have a pizza pie, okay, and there's 8 slices, how many slices can you predict with your treatment? Can you account for all of the slices or only some of them? The more variability that we can explain in a study, the better. Okay, that means that we know what's going on. We're able to predict what's going on. So when we come back into class at our next meeting, I'm definitely going to answer questions about this, conceptual, give some more examples in person on the board and that sort of a thing. But I want to introduce this concept of variance explained. It's a very popular measure of effect size. We will see it time and time again over the next couple of weeks. For now, you should have some idea what it's getting at, okay, and be able to calculate it. The calculation is straightforward. Okay, now we're going to go ahead and move into talking about confidence intervals. Okay, an alternative technique for describing the size of a treatment effect is to compute a confidence interval. Okay, a confidence interval is just a range of values that are sampled or centered around a sample statistic. Okay, the logic behind confidence intervals is really simple. It's the idea that a sample mean should be somewhat close to the population mean. Okay, that's because samples are supposed to represent the populations they come from. Therefore, we can confidently estimate that the value of the parameter, okay, the actual population mean, should be somewhere in that interval or range of values. Okay, a confidence interval is an alternative measure of effect size where we estimate the true population mean from the sample mean. And it's based on the reasonable assumption that, again, sample means should be close to the true population means. Why? Because samples represent their populations. For instance, if in my statistics course on exam 2, the class scores an 80% on average, I can be somewhat confident that the true population mean of all intro students in statistics is somewhere around 80. Okay, it's somewhere around that with a little bit of discrepancy in either direction possible. Okay, when we compute a confidence interval, it's going to be based on the estimated standard error of the mean. Okay, so every single sample mean has a corresponding t-value. Okay, so we're basically going to be locating a range of values using sample information that we can be somewhat confident the true population mean lies in. Okay, here's a figure from your textbook. This is the distribution of the t-statistic with the degrees of freedom of 8. Okay, notice that most of the t-values pile up around 0. Okay, 80% of all t-values are between negative 1.397 and positive 1.397. Every sample mean has a corresponding t-statistic, and we already know how to compute that. In order to calculate a confidence interval, this is the equation that you would use. We're just rearranging the equation. Okay, the true population mean is equal to the sample mean plus and minus the critical t-value times the standard error of the mean. Note this is the critical t-value from the table for that particular degree of freedom. It is not the t-value for the sample. It is the t-value from the statistical table. Okay, here's our infant study. Our true population mean is equal to 13 seconds, which is the sample mean, plus or minus the critical t-value from the t-table for degrees of freedom of 8, which is 1.397. Okay, if you use the table, you find 8 degrees of freedom, you scroll over, the critical t-value is 1.397, and the standard error of the mean in that study was 1. If we go through this math, we end up getting our upper and lower intervals. Okay, they end up being 14.397 and 11.603. What this is telling us is that in our sample, right, babies looked at the attractive face for 13 seconds, but the confidence interval tells us that the average time looking at the more attractive face for the entire population of infants is somewhere between 11.6 seconds and 14.39 seconds. And in this case, we are 80% confident that the true population mean is located in this interval. Okay, notice that we computed a confidence interval here for 80% confidence. Okay, if you look at your t-table, you'll see that different amounts of confidence are possible. There's 90% confidence. There's 95% confidence. As you get more confident, usually the range of values is going to become more spread out. Okay, so in order to calculate a confidence interval, you need to not only have your mean score for your sample, but you need to look up the critical t-value in the t-table associated with the level of confidence that you desire. Okay, you need to go through the math and you'll get your upper and lower boundaries. Okay, this is telling us that yes, in our sample, babies looked at the attractive face for 13 seconds, but in the true big population, it's somewhere between this. Okay, 11 and a half and 14 and a half seconds. So here is just some more text about using confidence intervals to estimate the population mean. Okay, for any sample, you have a mean, you have a standard error of the mean. You can pick the appropriate degree of confidence that you want to use. Okay, consult the t-table, find the value of t linked with that degrees of freedom and that confidence value. Go through the math, and you're going to get that resulting interval telling you that somewhere in that interval is where the true population mean lies. Okay, so you should know what a confidence interval is, and you should be able to calculate one. More confidence, higher confidence increases the interval width. Okay, if I'm 95% confident, I'm going to have to be willing to accept a wider interval than if I have lower confidence. Okay, that's going to make the interval shorter, but the chance of me being inaccurate about that goes higher. Okay, sample size is also important. The larger the sample, the better. Larger samples are better replications of the population. They're going to reduce standard error, and they're going to give us a smaller confidence interval, which is what we want. That means we're able to hone in and precisely identify a small range of values, and we know the population mean is in there. Okay, small samples increase standard error, And we're going to get a wider gap of values. Okay. Let me skip here. How do we report the t-statistic? Okay, very similar to Z. Okay, a couple changes, but very similar. We always want to report whether or not the test was significant. Okay, if the test is statistically significant, we reject the null. We have evidence that this sample is statistically different from the population that it was drawn from. However, if it's not significant, we failed to rule out the null hypothesis. Report the t-statistic, including the degrees of freedom. A t with 12 degrees of freedom came out to be 3.65. And then we report the significance level. Okay, if we reject the null hypothesis, our probability of a type 1 error is less than 5%. P is less than 0.05. However, if we fail to reject the null, we flip this sign. P is greater than 0.05, hence why it's not significant. Some researchers will give the exact probability that computer software spits out. Okay, so if you see that, that's all they're doing. But I prefer that you either indicate whether the chance of a type 1 error was greater or less than 5%. Okay, P less than 0.05 means we had a statistically significant result. We rejected the null. P greater than 0.05 failed to reject the null. Okay, in my course, I focus on two-tailed non-directional tests. They're the most commonly used, where we look for extreme cases at either end of the two tails. Again, though, we do have those directional tests in certain research situations where there's strong justification for predicting the direction of an effect. You may see those. Everything's exactly the same, but the critical region gets pushed to one side or the other. Okay, I'm not going to focus too much on them. I just want you to know that they're out there and that people do use them in certain situations, although they are less common. Okay, let's see if we can interpret the results of a t-test. Okay, the results of a hypothesis test are reported as follows. A t with 21 degrees of freedom came out to be 2.38. P is less than 0.05. What was the statistical decision and how big was the sample? Okay, take a minute to read through those. Okay, well, 21 people, we must have 22 in the sample. If degrees of freedom is 21, we must have 22 people, because degrees of freedom is n minus 1. If the probability of a type 1 error is less than 5%, it's statistically significant. Okay, the null hypothesis was rejected. This sample is significantly different from the population that it was drawn from, and there were 22 people in the study. True or false? Sample size has a great influence on measures of effect size. Okay, absolutely false. The entire point of effect size measures is that they do not, they're not contaminated by sample size. Okay, they are not influenced by the size of the sample. They give us a pure measure of how important or impactful that treatment or intervention was. When the value of the t-statistic is near 0, the null hypothesis should be rejected. Okay, false. When the value of t is near 0, that supports the null. It means there's basically no difference between your sample and the population. T-values near 0 are not significant. So here's a question I want to leave you with. Okay, this would be a great way to make sure you're on track. Okay, here's a question that is very similar to something you'll see on the next exam. I've given you sample data. Okay, a sample of 16 individuals are selected from a population. We're administering a treatment. We want to see if this treatment has changed them. Go ahead and compute a single sample t-test in order to evaluate whether or not the treatment has a significant effect. Then I want you to compute all 3 measures of effect size and interpret them. Compute Cohen's d and r squared, and then calculate a confidence interval for 95% confidence. Okay, you need to use your t-table to do that. Okay, use the confidence of 95%. And bring your answer to class We will start our class off with going through this problem together and making sure that we all understand it. Okay, my slides are uploaded in D2L, so you can also download them there. The solution is in the notes, but I encourage you to go ahead and see if you can do this on your own. Okay, if you can solve this problem correctly, you're totally where you should be right now. Okay, so that's going to wrap up this video. Please bring your response to this question to our next class, and I will be seeing all of you soon. Okay,